In this lecture, we're going to solve for an unknown quantity in a problem by starting from the angular momentum principle in a multiparticle form. We'll also apply other fundamental principles, Newton's second law and the energy principle, to solve for other unknowns. This will serve as a nice example where we can bring all three principles to bear in the same motion situation. Here's the example. A stick of mass big M and length L is initially lying at rest on a sheet of ice, which we'll consider to be a frictionless surface. A hockey puck of mass little m is initially moving with speed v sub I when it strikes the stick a distance d from the stick's center of mass, and the puck bounces off the stick with a speed v sub f. The puck strikes the stick at an angle of theta sub I and bounces off at an angle theta sub f, where the angles are measured from the negative x direction as shown in the figure. We want to first find the vector omega sub sf, the vector angular velocity of the stick about its center of mass after the collision. Just to be clear, we will find this angular velocity in terms of the known quantities, which are the length L, the masses big M and little m, the speeds v sub I and v sub f, the angles theta sub I and theta sub f, and the distance d. To do this, we'll need to apply our multiparticle angular momentum principle, where we choose as our system the stick and the puck together. Now, if the surroundings exert no net twists on the system, then the net torque on our system is zero. And this means the total change in system angular momentum must be zero, or equivalently, the total final system angular momentum must be equal to the total initial system angular momentum. So, our next step is to write down expressions for these total angular momenta. The total system angular momentum initially is the vector sum of the total angular momenta of the stick and the puck. As always, with rotational quantities, we need to choose the location of our axis. A good choice here is to take the location of the stick's center of mass prior to the collision as our axis location. We'll use this choice for computing all rotational quantities in this example. Now, the total angular momentum of the stick is initially zero because it is neither translating nor rotating. The total angular momentum of the puck is due to its translational angular momentum. In this example, we'll assume the puck is so compact that it's effectively a point particle and therefore has no rotational angular momentum. Now, to compute the puck's initial translational angular momentum, we'll do this by visualizing the situation just before the collision, as we show here, and taking the cross product of the puck's position vector with its momentum vector. The magnitude of the puck's initial translational angular momentum can be thought of as the product of the magnitude of the position vector, which is just the distance d, times the magnitude of the linear momentum component perpendicular to the position vector, which is little m times v sub I times the cosine of the angle theta sub I. By doing the right-hand rule, we can see the direction of the puck's initial translational angular momentum is into the page, the direction of the minus z-axis here. So putting this all together, we can write down the total system angular momentum initially as shown here. We now focus on the final total system angular momentum, which is the sum of the final total angular momenta of the stick and the puck. We visualize this at the instant just after the collision, as shown here, and choose again the same axis location, the stick's center of mass prior to the collision. We compute the total final angular momentum of the puck the same way we did with the initial. We assume that puck's total final angular momentum is all translational, and we compute the appropriate cross product here to find both the magnitude and direction. Notice here the puck's final angular momentum is pointed in the positive z direction when the angle theta sub f is less than pi over 2 radians as shown here. Now we also need to compute the stick's total angular momentum after the collision, which will be non-zero. The stick itself is an extended multiparticle object, so we'd expect that the total angular momentum would include both translational and rotational angular momenta contributions. However, for our choice of axis as the initial location of the stick's center of mass, the stick's translational angular momentum will be 0. One way you can think of this is the stick's linear momentum p will always have a line of action that passes through our choice of axis. Thus, the moment arm is 0 when we choose the axis as the initial center of mass of the stick, and so the stick's translational angular momentum will also be 0. So we only need to compute the stick's rotational angular momentum after the collision, which we can write as the product of the stick's center of mass moment of inertia, I sub s, times the stick's final angular velocity, omega sub sf, which is the unknown quantity we're trying to find. The stick's moment of inertia will be 1/12 times big M times the square of the stick's length, L squared. Now we're in a position to plug all these results into our angular momentum principle, which says that for this case, the total final system angular momentum must be equal to the total initial system angular momentum. We'll write out only the z components here because we only have non-zero components along the z-axis. And we can see that we have only one unknown, omega sub sf, z component. So we solve for that to obtain this final result. Now that we're on a roll, let's keep going and apply our other fundamental principles to solve for other unknowns. We can apply Newton's second law to solve for the stick's linear velocity, big V sub f, after the collision. So let's do that. Now if the surroundings exert no net pushes or pulls on the system, where our system consists again of the stick plus the puck, then we have 0 net force on the system. This means the change of the system momentum must be 0, or equivalently, the initial system momentum before the collision must be equal to the final system momentum after the collision. Let's write out each of these system momenta in turn. The initial total system momentum will be the sums of the initial momenta of the stick and the puck. The stick is initially at rest, so it has 0 initial momentum, and the puck's momentum will be just the product of its mass times its initial velocity. All these quantities are known, so the initial total system momentum is known. The total system momentum after the collision will be the sums of the final momenta of the stick and the puck. Both of these are non-zero. The puck's final momentum is known. It's the product of little m times the final velocity, which is known. The stick's final momentum will be big M times our unknown, the stick's final center of mass velocity, big V sub f. We can collect all these results together now and solve for our unknown velocity, which we can further write out in terms of x and y components with the choice of coordinate system as shown. Finally, we can now apply our energy principle to solve for one more unknown, the change in system internal energy, which we'll assume to be thermal. If we assume there are no transfers of energy into or out of our system, then the change of the total system energy is 0. Here, there are two contributions to that change: the change in the total system kinetic energy and the change in the system's thermal energy. So if we find the change in the total system kinetic energy, we can solve for the change in the system's thermal energy. There are three distinct kinetic energy changes: the change in the puck's translational kinetic energy, the change in the stick's translational kinetic energy, and the change in the stick's rotational kinetic energy. In all these cases, we're comparing the initial state of the system before the collision to the final state of the system after the collision. We have written out all these kinetic energy changes here. So now we can collect these results and solve for our final unknown, the change in the system thermal energy, as we show here. Now, as an exercise that you may want to do on your own, you may want to replace the variables big V sub f and omega sub sf with the expressions we found earlier in this lecture. Before that, let's make one final comment here to end this lecture. Notice what this result tells us. It says that if we start with the total initial energy of the system, which is the initial kinetic energy of the puck, and we subtract off all the kinetic energies after the collision, the puck's final translational kinetic energy, and the stick's final translational and rotational kinetic energies, then whatever is left over has gone to increase the system's thermal energy.